Okay, dear students, we are going to discuss the concept of Hermitian matrix. Hermitian matrix. Now, the definition. If a square matrix, capital A, is said to be Hermitian matrix, said to be a Hermitian matrix, said to be a Hermitian matrix, then A power theta is equal to A power theta is equal to A, where A power theta is equal to conjugate of a transpose of a conjugate matrix, and A bar is nothing but conjugate of A. Conjugate matrix of A. Conjugate matrix of A. Conjugate matrix of A. So this is the definition for Hermitian matrix. Okay. If a square matrix, capital A, is said to be a Hermitian matrix, then A power theta is equal to A, where A power theta is nothing but conjugate of a transpose. The symbol of conjugate, that is A bar represents conjugate matrix of A. Right? This is the definition. So this can be represents also. Let capital A is equal to Aij. This is the representation of the matrix of order n by n. That means square matrix. That's why this is the element in the matrix, ith row, jth column element, that is square matrix of order n. Then A power theta is equal to A, such that Aij is equal to A bar Ji, where A bar means conjugate of the matrix. This is conjugate of the element. Okay, for all I comma j. That's all. Now this is the concept for Hermitian matrix. Now we have to take example for this one. Example. Take the square matrix. Let A is equal to 1, 2 minus 3i, 3 plus 4i, 2 plus 3i, 0, 4 plus 5i, 4 minus 5, 3 minus 4i, 4 plus 5i, 2. So this is A. Now to find A bar, that means conjugate of A, that implies A bar is equal to. A bar means we have to write conjugate of the complex number. That's why in this matrix, in this square matrix, involving the elements are complex numbers. Complex numbers. That's why complex number is always in the form of a plus ib. That's why a plus ib is the complex number where a is a real part and b is imaginary part. And a and b are real numbers. That's the conjugate of a plus ib is nothing but a minus ib. Conjugate of a plus ib is a minus ib. Now we have to write conjugate of this matrix. That means we have to write for conjugate complex numbers, we have to write conjugate complex numbers. That's why a bar is equal to, here it is 1, here it is 2 plus 3i. Since a plus ib conjugate is a minus ib, that's why 2 minus the 3i conjugate is 2 plus 3i. Here it is 3 minus 4i. 3 minus 4i. Here it is 2 minus 3i. Here it is 0. Here it is 4 plus 5i. Here it is 3 plus 4i. Since we have to write the conjugates, here it is 4 minus 5i. Here it is 2. This is conjugate of the matrix. Now we have to transpose of conjugate. Transpose of this. A transpose. A bar transpose. A bar transpose. This is nothing but a power theta. So a power theta is equal to, it's a transpose. Transpose means we have to interchange the rows and columns. That is 1, 2 minus 3i. 3 plus 4i, since this column into place of first row. Now second column, 2 plus 3i, 0, 4 minus 5i. Third column, 3 minus 4i, 4 plus 5i, 2. That's all. These two same. So we get a. That's all. That's why a power theta is equal to a. So this is the concept of Hermitian matrix. What's the definition of the Hermitian matrix? If a square matrix capital A is said to be Hermitian matrix, then a power theta is equal to a. Where a power theta is nothing but conjugate of a transpose. Conjugate of a transpose. Okay, conjugate of a transpose. That's why it's conjugate of a. It represents a bar. That's why definitely in the matrix involving complex numbers, where we have to find the complex numbers, for a bar we have to write conjugate complex numbers. Conjugate of a plus ib is nothing but a minus ib. That's all. So conjugate transpose is nothing but a power theta. It gives a. That's it. Okay. So this is the complete concept of Hermitian matrix. Now note for this one. Note. Write note. Note. All the principal diagonal elements. All the principal diagonal elements all the principal diagonal elements of a Hermitian matrix must be purely real. Of a Hermitian matrix. Of a Hermitian matrix. Of a Hermitian matrix must be real. Must be purely real. Must be purely real. Purely real numbers. That's all. Observe. So this is Hermitian matrix since A power theta is equal to A. Observe the principal diagonal elements 1, 0, 2, 1, 0, 2, 1, 0, 2. These are all purely real numbers. Purely real numbers. That's why all the principal diagonal, this is the one of the representations actually in Hermitian matrix. Definitely in principal diagonal elements purely real. Okay, that's all.